I'd like to thank you for inviting me to give this talk. I know that most of you are probably not familiar with this field as much, so I'll just give a brief idea of how it's related and what I can see from the STATMIC point of view. For system with degeneracies, we know that interactions can lift the degeneracies and select a particular state. And basically, you can have many competing phases. And depending on the details of the interactions, you can have different kinds of symmetry breaking. So what I would like to argue is that the graphene quantum Hall effect at filling factor nu is 0 is a clean realization of such a system. For those who are not familiar with graphene quantum Hall effect, it's just that you have a single layer of graphene sheet and you put a perpendicular magnetic field, and basically the low energy states get reorganized into Landau levels. And what we are interested here is in the 0th Landau level, and which has a 4-fold degeneracy. So it has 2 spins and 2 valleys. So essentially it's like a 4-component spin system. And exactly at nu is equal to 0, 2 out of these 4 states are filled. So that's the reason that you can have many possible ground states. There is no kinetic energy, so the kinetic energy is quenched. So physics in this lowest, in the 0th Landau level is basically selected only by interactions. So the problem that one has is that there are different ways of arranging the spin and valley degrees of freedom, and they can lead to different ordered phases, such as canted antiferro. I'll just mention what these things are: canted antiferromagnet, polarized, charge ordered. But many of these phases are actually, if you do charge transport, you'll get the same results. So we wanted to see how to experimentally distinguish which order is realized. So for instance, the phase diagram at nu is 0. You can have a ferromagnetic state where the spins are ordered, or a canted antiferromagnetic state. Both of these are spin order. You can also have valley ordered states like Kekule distorted as CDW. These are all different ways of breaking the SU4 spin valley symmetry of the system. And which of these states is realized will depend on the Z1 energy, the valley anisotropy, and various other short-range interactions in the system. So, okay, just as an aside, let me also mention that you can even have coexistent states, which we worked on a while ago, but I'm not going to talk about that, so I won't say anything more about that here. What we wanted to say is that can one use magnons as a probe of trying to find out which of the ground states is realized? And magnons are essentially collective spin excitations. And by studying how magnons propagate through these states, one can try to see which of these ground states is realized and study the nature of the ordered phase. So in quantum Hall systems, essentially people can create magnons at the contacts by having potential difference between or counter-propagating states, and then they will go through some kind of a sandwich. You can create them on one side, you have the system you want to probe, and then you have the other, detect them on the other side. And this is something which can be experimentally done. So what we did was considered a 1-1 junction, and we put in magnons are injected from the polarized news 1 region. They propagate towards the central region, and then at each of these interfaces you have scattering. You can have either reflection or transmission, and this will actually probe the order in the central region. That was the idea. And the key point is that these interfaces can actually rotate either the spin or the valley. And depending on that, you can see whether the magnons can transport through it or not. So that will what gives us the underlying order in the system. And since the magnons carry spin, we can see whether it transmits or not transmit, depends on whether the ordered phase is spin ordered phase or not. So, okay, this is just one slide to say that what we do, we actually study it using something called time-dependent Hartree-Fock setup formalism. You can do reflection transmission, but there are equations which you can set up for that. And you send in the spin magnons from x's minus infinity. At junction, they mix with the spin magnon and spin valley magnon, and then they detect it at x going to minus infinity at the other end. And roughly the interface region, because we are changing between 1 and -1, that can be thought of as a nu is equal to 0 region. So depending on whether the interface involves spin or valley rotation, it corresponds to different spin breaking in that state. So what we find, our results, is that we can either have zero transmission or you can have totally full transmission. There that you have a binary result, either zero transmission through the, so depending on whether the spin rotates, then the ground state breaks valley symmetry. If the valley rotates, then you get perfect transmission and the ground states break spin symmetry. You get a spin symmetry ground state. So, and then what is more important, we can also tune because of the fact that the spin Zeeman and the interaction terms are proportional to the magnetic field, whereas the valley Zeeman does not depend on the magnetic field. You can actually tune between these two phases. So it drives transitions between the two regimes, one with perfect transmission, which is a spin magnet, and one with zero transmission, which is a valley magnet. So that's the central message that I wanted to give here, that Magnon transmission, when you have many states at nu is equal to 0, which can be either spin ordered or Magnon or valley ordered, by sending Magnons through the system, you can actually find out what kind of order that the ground state has. Thank you.
Thanks, Sumathi. We have time for questions.
Is it possible that none of these orders exist in the system because they keep fluctuating?
What?
It is possible that none of these particular orders exist because they keep fluctuating between them?
None of these orders exist. Okay, I mean, the point is, yeah, all of these are Hartree-Fock order. And so you're putting in the order and you're checking what the ground state energy. There can be an order which is realized, which has not been considered. But it is, and what we are also doing is what the time-dependent Hartree-Fock does is also you're taking care of fluctuations beyond Hartree-Fock. But certainly these are not exact calculations, and if none of these things, it is Hartree-Fock.